Tá bom a posição, gente? Então, eu vou explicando, mas eventualmente eu volto pro meu computador para criar alguma coisa. Mas não tem problema se eu sair de quadro. Eu não,
Agora acho que vai pegar direitinho.
É que eu não consigo puxar mais para cá por causa do gato HDMI.
Não, tá tranquilo. Assim ficou perfeito.
E deixa eu só ver o que tá faltando. A minha voz é foda, né, gente? Essa minha voz em gravação sempre fica uma coisa...
Eu queria aparecer em imagem.
Ah, nem falha, eu sempre fui, né? Ah, deixa eu ver o que falta. Eu de novo, Danilo. Agora eu vou no banheiro rapidinho. Tá. E aí, uma última pedido, gente. Nós temos alguma coisa para eu escrever no quadro? Eu sou professora, né? Eu gosto de escrever no quadro, sabe como é que era? Alguma... Só não traz uma permanente. Ainda falta 10 minutinhos, mas só para eu saber, alguém não fala português? Se sente melhor com inglês? Everybody speaks Portuguese? Okay? Is Portuguese okay for everyone? Okay? Damile. Desculpa, Damile. Só para confirmar. Até que horas nós vamos?
Até que horas?
Uhum.
O quanto for necessário.
Posso ir?
Tudo X. Avisado que às 3h45 dele.
3h45, tá.
Precisar ser...
Não, que daí eu me programo para terminar isso. Para terminar às 3h45.
Porque eu tinha colocado umas horas e meia.
Tá.
Assim, a gente...
Eu me arranjo.
Tá. O pessoal conversou com o desenho. Ele falou que...
Agora me contradizendo, Damile acabou de me avisar que por causa da transmissão online, a organização pediu que seja em inglês, ok? Então eu falarei em inglês, mas por favor fiquem à vontade, caso você não entenda, é só levantar a mão, pedir para eu repetir, que eu repito em português, para ficar claro, ok? Mas para manter o que a organização nos pediu para deixar a transmissão em inglês, eu falarei em inglês, ok? Vou falar mais devagar, mas por favor, fiquem à vontade, não entendeu, não fique com vergonha, só levantar a mão e falar não entendi, que eu repito em português e a gente já resolve. Perfeito? Todos prontos? Everybody ready? Okay. Okay. So we're going to be starting now the workshop or tutorial about thermal analysis with thermal desktop from ANSYS today, okay? Just to present myself real quick, my name is Talita. I'm a professor at Federal University of Santa Catarina, in Santa Catarina, a little far from here. And I work in this area of thermal analysis for different applications, oil and gas, petroleum, and industrial equipment, and satellites. So today, I'm going to be presenting a little how the thermal desktop software works for applications with space applications, okay? That's the idea. Please feel free to ask questions at any time, okay? This is the interface of thermal desktop. I'm just gonna be showing you a little what we are going to be looking at the end of this tutorial, and then we are going to be starting from the beginning, okay? This software, I don't know if you are aware, thermal desktop is the software that nowadays ESA and NASA use, okay? It's, as far as I'm aware, it's one of the most used softwares for space applications. So it's a very good software. In Brazil now, they have a commercial representative. It's, in Portuguese, we say E3S. In English, it would be ESSS, is the seller of the software. They sell also all models from ANSYS, okay, CFD, mechanical, all these models. STK from orbital analysis, they are the seller, okay? And now they sell this one. We have bought this thermal desktop license for our lab in Santa Catarina. Nowadays, my students are learning to use it, and I actually like it very much. That's why I decided to have a little tutorial about it. It's very good, but it's a little complicated. It's not so user-friendly as ANSYS usually. Okay, that's the idea. So what I have here, just to have an idea, it's a very simple example. Since we only have 1 hour and a half, we're gonna be applying to a simple, a 1U CubeSat in orbit. It's one of the most basic applications, okay? You can do a lot more. They use it for the International Space Station, okay? You can do a lot of things, but this is a basic example that covers all the basic applications you need to know to make it work. So what you can see here, it's an 1U CubeSat, 10 centimeters, 10 centimeters, 10 centimeters, something like this, okay? Very simple. It has a little battery inside. You can see here a little cube. Let me change the wireframe. Here we are seeing the wireframe. Here is 3D model. And just so you can see inside, let me just sorry. You can and one back. In order, I'm going to be say expect one color applications. So you can see my folder. I created one. Inside here, I have created. Inside the project, I the only way to use. I use to create a template for myself. Template. With the license of Terminal Desktop, if you that's free university of that when you're going to buy from E3S. They are not going to be selling you the Autodesk license. If you do not have, you cannot use Terminal Desktop, okay? So You have to think ahead of I could do this. Then I would have to draw this. If I'm looking for this kind of detail, I would do this. Okay? But since I have already used this software and compared to real results, I know that if I do this, or if I do simply this, it's the same result for this application. Because I'm not doing anything different. I'm going to be using classic space materials with not a new geometry or nothing like that. So I'm just interested in the parameters. So I can use a simplified surface that's just a rectangular. Okay? Just to be clear, usually what we do, okay, when you are in the design phase of a CubeSat, you're going to be using these simple geometries because you don't know a lot of the inside of the satellite. So there's no reason to just try to find a different application. You just need the maximum and minimum temperatures so you can actually do the preliminary design and then put the battery and heat tubs and something. And then you're going to be doing a more specific drawing. Just 1 second, because I think the cable is not going. Technical support. Devo resetar? Okay. While you have a technical support, okay, just to be clear, usually we do this for the first design, what we call the preliminary design. You are in the mission design phase, okay? That's a good design. When you go to the critical design phase, later on, when you go to a critical design phase, you are going to be doing something more specific because you are looking for little details, okay? But it's the same idea. You are just going to be using your simulation and changing the geometry. Here, I'm just going to be using normal geometry because it's the same thing that you have to do the thermal analysis. Okay, so if you are later on in the final phase, you should actually do a more complex geometry. Nunca fiz. Peraí, sai daqui, ó. Fecha esse. Aqui eu acho que tu vai conseguir cair na tela. Oi? Peraí. Fui falando exibição. Opa!
Falaram, orientaram pra gente tirar o cabo.
Tirei e coloquei de volta.
E o Windows P.
Windows P? Vai lá.
Aqui, ó. Isso. Tela do computador. Duplicar.
Duplicar. Foi? Windows P. É, eu ponho, mas ele não foi. Vai lá.
Então, eu vou chamar a assistência.
Se puder. Esse é o cabo. Uhum. Deixa eu tentar um negócio aqui. Clássico. Tira o cabo e põe de volta, por favor. Pode botar. Tentei, mas não foi. Então.
Normalmente.
Opa. Ah, mas agora ele foi para o PC. Deixa eu trocar agora. Agora tira e põe de volta. A última vez a Damile fez isso. Pode botar de volta agora. Sucesso! Beleza. Tá ótimo. Voltamos. Okay. Sorry for the delay, everybody. Technical problems. It happens, yes. Okay, so we are here. So the thermal model, you can see you can actually do. I'm going to do a little rectangle. You can see AutoCAD works for coordinates. So if you have more than 40 years, you know how to do this. But if you are younger, actually, you are more familiar with SolidWorks. That's a little different. But here you can see the coordinates. Okay, so you actually put 0, 0, 0, 0, 1, something. You can do like that. But they do have something for newer generations that you can click for the origin. So I'm going to say the origin is 0, 0. Then he's put, okay, your first point. Here I can actually put, if you put 0, 0 here, he understands you're going to be starting 0, 0, 0. And then you can actually put points, each point, or just try to draw. I'm going to be doing the first point. So if I want a CubeSat 1U, it would be 0 for X and 0.1 for Y. So here, okay, he says, okay, you are telling me 0, 0, 0, 0, 0.1, and 0 in X. And here you can draw. So here, if I just click on the screen, it's going to close the rectangle for me. I'm going to close here. And he opens the panel for each time you draw something, he opens this panel for surface. So here, he's saying to me, okay, you have a rectangle. In the X direction, you have one node. In the Y direction, you have one node, 1 per 1. This configuration here. One simple node. And you have X and Y. I'm going to be starting with this one because we can actually just update after, okay? But if I put here 3 and 3, it's going to be 9 nodes, 3 per 3, and so on, okay? So this is 1 by 1. And now you have a lot of configurations here. Numbering. You do have to actually remember to use numbers for each node you create. So if you do not use different IDs, the software is not going to be doing it for you. Like I said, it's not a user-friendly software, okay? You have to actually remember, I'm creating 3 nodes. I have to tell him which one is 1, which one is 2, which one is 3, okay? So this one for me is the 1, is the first node. The submodel, you have to tell him, okay, what's the name? This is in what submodel. I'm going to be using only one model here because it's a submodel called solar panel. And then I would go here, say solar panel. I'm just going to be using man here. In my templates, my final templates, I'm going to be showing you that I have different submodels because I like to be more detailed, okay? Now you don't have it because it's very simple. So it's just a submodel. I have to tell him the radiation. This is the best part of the software and also the most critical one. Thermal desktop is used by NASA and ESA for space applications because he has a very good radiation model, okay? For orbit configurations and for normal radiation. So this is the best part of the software, but also the most complex because you have to understand a little of radiation phenomena, okay? I'm not going to be using now. We are going to be going back here after I explain to you how to configure this, okay? But he has, each surface I create, he has, okay, you have to tell me which surface is going to be exchanging heat through radiation with which one, okay? I'm not going to be using now, but we're going to be back here later. Now I'm just going to actually, you have the material. I'm not going to be using material now. If you want to put installation, no installation. Here. I'm just going to confirm in the surface tab that I want to create my little further. you come here and you adjust it, okay? Usually we do that to make sure the satellite objective has exactly the configuration needed. So here I just change, okay, it's not 0.11, it's 0.1, okay. And then I do okay. You can change it after if you want, okay? But here I have my one face, the first one. You can see a little note because I said it's one note. Thermal desktop is a finite difference based. So use nodes for configurations, okay? Now I'm just gonna create the others. Yes.
You mentioned about radiation for thermal.
Yes.
But does it include also conduction?
Yes.
But it's not there.
It is there, but it didn't change it.
Okay.
Good question. If I double click, he's going to be opening the same tab for me, the tab for this surface, okay? You do have a tab for condition configuration. Okay. I didn't change it yet because I didn't create the material. I'm going to be creating, and then I go back here and say, okay, this is material. But you're right, because what is finite difference? Finite difference is something we in exchanger. Distance. Idea. If you can a solid is a conductance. What is conductance? One that you find other software. Okay, but it's going to be so. This is each tab is one. The conduction transfer, and the other is. You do have convection also. Also, but certified would not actually action. But you. So this is my first. Already the 6 surfaces, okay? So now you just do the same thing for each surface. I'm just going to be closing this one because we're not going to be using again. And I'm going to be open again because if you remember, I just erased the first one. Here you have the 6 face, each one with one node. This is the geometry, only the geometry. Okay. Now, what I should do is tell the software which material this is. It's aluminum, it's solar panel, what it is, okay? So you go to thermal, again, you see only the thermal tab. And I go to thermal physical properties, edit property. If you do that, it's going to be open, this panel, that we already have some materials because I already did this workshop, this tutorial at home to see if it was going to work now. So I have, you come here and you actually input your material. Which material do you want to work? So if I want to do something like a test, just a test, something that I want to call, you put the name, you do add, and he's going to be asking you, okay, give me the properties of the materials. K is conductivity, is for the conductance, okay? This is a normal thermal conduction material. Watts per meter per Kelvin. If you have iron, that's a metal, you're going to be having a high conductance because it conducts heat transfer through the iron. If you have something like insulation, it's going to be having a small value, 0.1. So this is actually the value that you have in most handbooks for space applications of each material. Okay, this is very easy to find. This is just the default, it's 1. Okay, we're going to be using actually the ones I have here. You can tell if it's isotropic, anisotropic for guys from material engineering. If you have actually material composite materials, you have anisotropy and so on. Usually in space applications is isotropic. It's the same value each direction. That's actually what we have. Specific heat. This is joules kilogram Kelvin. How much energy can this material absorb before it increases its temperature? If you have water, you have a specific heat of 4,182, if I'm correct. So you have to actually input 4,182 joules of energy before it changes 1 degree. That's the idea, okay? So if this number is very high, it's going to be changing the temperature. It's going to be changing less temperature. If it's very low, it's going to be changing the temperature very fast. That's the idea. It's a common property of material, okay? Density, everybody knows what density is, okay? And you have effective emissivity. This effective emissivity is when you are using not a real material, because then we use the emissivity, radiation emissivity. This is for something that it's actually, I don't remember the word in English. Does everybody know how we say película in English?
Film.
Film. Yes, thank you. You have a film, just a film. Usually we use for space applications for reflective films. Okay, you have that gold film that you put in space applications. It's a radiation that it's reflected. Usually here we're not going to be using because it's just for film applications. I'm going to be using the real emissivity of the material. This is the material. When you input the properties here, then you go okay, and he's going to be creating here. We are going to be using the ones that are already created. We have aluminum. SHIP is the name I did it for electronic components. Okay. This is a copper. It's a different metal. And we have MLI that we usually use for insulation. Okay. You can actually put the ones you want. This is a simple application, so we can choose one. You have the conductance. You have this specific heat. Okay. And you have the density. So this is the materials for him. So when I do this, the software understands you are going to be using something of this one. And then I go back in my geometry and I say, okay, this surface is this material. Then I just do okay. Now he understands. And I go one. I didn't use that. And here, okay. This is using a submodel that I created as call it solar. You could use the same submodel. You can see here that I put it, this is aluminum. You can choose whatever. This surface is aluminum, okay? And I say the thickness is 0.02 meters. This surface is set. I can use different configurations, okay? This is just an example. So this is the conducts. You do that for everyone. If you do not want to do one by one, you have this model tree. After you are actually familiar with the software, we use this model tree. It indicates everything that I've done. So in the last example, the name was main. This I just call solar. You have 1, 2, 3, 4, 5, 6 nodes, one for each face. It's just a geometry tree. I can do everything by here also. If I want to change all nodes together, I just go here, edit, and ask, okay, what we're saying? You are changing the surface or the node? I'm changing the surface. That panel that just opened is the surface panel. So I go here and I say, okay, change. You can for me. Are you changing the 6 surface? Maybe the resolution is not so good, but there's a 6 here. Are you trying to edit all the 6 surface all together? Yes. If you go here, you're going to be going to the same panel. But if I modify here, it's going to be actually modifying for all 6 configurations. When you are more familiar with the software, you usually do a lot of bundle like this. Okay. This is the conductance. So right now, the software understands that I have 6 surfaces and they are all aluminum. Okay. The strong feature of this software is the radiation. So let's go for where if you don't know how to set it, it's going to be going to errors. So just to explain very radiation. This is a very simple design. So we have actually radiation heat transfer. if you are not aware, is one of the three phenomena of heat transfer. We have conduction, solid by solid. We have convection, solid by fluid. And we have radiation, surface through surface, by space. That's the idea. So radiation, you have radiation. If I have a surface here, and I have a surface here, if there's nothing blocking it, this one is actually going to be exchanging radiation with everything it sees. So this surface and this surface exchange radiation. This is what we call view factor and so on. This software has a model of view factors, okay? So when I draw the geometry, he's going to be calculating this for me, so I do not have to calculate. He uses Monte Carlo's model. It's a model for statistics. So what he does is, I've drawn this surface and this surface. The software understands that this surface has this geometry, and then he's going to be setting a lot of rays. So he traces the ray, and he understands, okay, if I have 5 rays coming from this surface, and one of them reach here, the view factor is going to be 1 divided by 5. If you shoot 1 million of rays, you're going to be having a lot of more rays that actually collide with the other surface, and it calculates. A higher number of rays, the best result you have for radiation. That's the idea. All of this the software does for you. You do not have to worry, okay? What you have to worry, I have to actually say to the software that this surface and this surface have a clear path for radiation. It's not blocked. The user have to say it. If I just draw this and say, go, he's not going to go. Because I have to say, this one and this one exchange. How much? I don't know. You calculate. But they do exchange. That's what we call radiation analysis groups. And you have to, the user has to manually set it. So you have to understand a little of radiation so for this to work, okay? For us, what would we have to actually set up for space applications? Our application, it's an easy radiation application because you have a cube, a closed cube. So I'm going to be drawing a 2D, okay, of the cube. So we have the internal face, and we have the external. This is a classic problem, I only have 2 possibilities for the radiation. It's going to be exchanging inside or outside. That's the only possibility. Because this is a surface, but this side of the surface, the internal side, is going to be shooting rays. Here, 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 here. But the rays are not going to be going outside because there is no hole. There's not a cavity, no, okay? There's no opening. The other side is going to be shooting for the space. So we have the external radiation, and we have the internal. And I have to tell him. That's the idea, okay? If you do not do that, it's going to create an error, and it's not going to go on. This is actually what I consider the most common part where the user usually makes a mistake to indicate this one. It's very easy if you can see this. This one is going to exchange with this, with this, with this. It's internal. No rays is going to be coming out because the radiation, when it comes from this and it collides with this, the radiation, it's like light. If you point a laser to the wall, it's not going to be going through the wall. It's going to be stopping on the wall. That's the radiation, okay? And this side is going to be emitting radiation outside. That's the idea. So we create in this problem, 2 radiation analysis groups, the internal and the external. And I tell him which one is which, okay? So that's what we do when I go to thermal. And we have here, radiation analysis group. When I click here, I have to tell him, okay, we have 2 radiation groups, internal and external. This is the radiation analysis group. You can see there's already an external and internal here in Portuguese, because I did it, okay? Usually the default is external and internal. since most applications are space applications, the default software is to have what he calls external and internal. You can just edit it, okay? I erased it and created the external and internal. Look, this tab is just for the name. I'm just saying there's two radiation groups, the external and the internal, just that, okay? I didn't say which one is which one, but this problem there has only two radiation groups, okay? This is just comments, okay? I'm just doing comments. Radiation from faces to the space ambient, space environment, radiation's internal. It's just that, just for curiosity. If you have a refrigerator, freezer and the one, okay? If this is your refrigerator, you have here one radiation group, because this one's going to be exchanging like this. We have two, and you have three. So each problem you have to analyze how many radiation groups I have. How many cavities do I have? You have one cavity, two cavities, and the big one, three cavities. Okay, so each problem you have to analyze. CubeSats usually have two, internal and external. But just remember, if I want to use a board here and a here, I would have 1, 2, 3, and 4 radiation groups. Okay? If you actually close the cavity, it's a radiation group. If it's open, it's not a radiation group. If I use something like this, 1, 2, 3. This is radiation analysis groups. Okay, that's what you have to tell the software. For us, it's just internal, external. The idea is okay? Okay? This is actually the step that most users usually have more difficulty. Here, the radiation analysis group is just the name. So I tell external, internal. Okay. And now I go back to my geometry in the radiation tab and I tell him which one is internal and which one is external. Because I said there is two radiation groups. Now I have to tell him, this is external, this is internal, because he does not know, okay? Just double click each surface and tell him. So I'm going to be double clicking the first one. It's the same tab. So we have the subdivision, one node, the number, okay? This actually is probably not the one. Since I have 6, this is the 4, okay? Number 4, radiation. Here I have to tell him. Here's the radiation tab. You can see that actually it already indicates for me. You have the base. The base is if you do not input anything. The base is just the reference for me. You have the external, you have the internal. And then he asks me, okay, which one is top, which one is bottom, or in and out, because he knows that you only have 2 sides. Each surface has 2 sides. So he's asking me, this is external or internal, and so on. The top and bottom is a configuration of the software. Okay? He tells me this is top and this is bottom. You just have to indicate top is external, bottom is internal. If you do that, everything's okay. So, I'm going. Yeah, no. That's a good question because the first time I was using, I didn't know because it's very confused. The user manual of the software tells me, okay, that when you have the axis, so you have X. What the user manual tells me is that when you have a surface that's pointing to the positive direction, it's top. So if I'm looking for the top one, the user tells me this is top, and this is bottom. But it does not work every time. So I have you can do a cross check. Yes, it does. Sometimes it goes wrong. So I do use this as a normal configuration. If it's pointing to the positive, it's top. If it's pointing to the bottom, it's not. But I'm going to show you how to cross-check that and change it. So here, I'm just going to put the contrary. Okay, this is already set because it's my tutorial. But I'm going to say, okay, external. I double-click external. And then he opens this. Okay, choose the active side. Okay, external. It's my configuration. He tells me, okay, external, it's what for you? It's top, it's bottom, it's both of them. You do have configurations in radiation when surface exchange for both sides, okay? It's none of them. do not is do not exchange radiation. Sometimes you are doing a modeling that you do not want to exchange radiation. You should not use thermal desktop then, I should say, but you can choose not to use radiation, okay? And not in this analysis group. I do not want to use in this case, but I will be using after. So these two is not using. This is both of them, and this is upside and downside. Here is stop, because I know it's stop, but I'm going to change to bottom just to go the wrong way, okay? So let's say I don't know if stop is bottom. I know it's one of them. For me, I'm looking this one. I know I want external. What I think is stop, okay? I'm going to change to bottom because I know that stop, so just to go wrong. And I go there and say, okay, you told me that external for the top surface is bottom. And then he asks, okay, tell me what's the material of the surface on top and what's the material of the surface on bottom. Here I just call a solar panel material, but actually you can input different materials. So I have a super radiator, white paint, etc. I'm just going to be showing you what is. This is the radiation property of each materials. The tab that we did for properties was conductive materials. I didn't input radiation materials. I have to create a different tab for radiation materials. Here I'm just going to be using any one of them, okay? And then we're going to be showing. So this I'm using solar panels material because I want to use solar panel materials. And I'm saying, here is solar panels and here are solar panels. This is not true, but this is just a simple case to show, okay? I could use different configurations, like solar panel up and white paint down. So solar panel, white paint. You can set anyone. So this is the first. And then he say, okay, now tell me internal. What is internal? Usually, external and internal are different sides. So if I prescribe bottom as external, I'm going to prescribe top as external. If you just prescribe something that's possible, okay? So I cannot say that both surfaces are going to be radiation for both sides. That's not possible. The software is going to crash. So I said one side is outside, it's external, and one side is internal. That's the idea. That one is set. Okay, I have to do that for each one of them. Just double click and do it. I already do it. So I go there, top and bottom, everything's okay. And the idea is, okay, how can I make sure that I've actually got it right, the top and bottom? You go to thermal and you do a model check. The model check is there actually to see if you have the right input. So I go to active display preference, okay? And here he tells me, okay, face or by arrow, by color. By color code he uses. Surface, I got it. I want to see external. You can have green. These both. This is that green. Showing this face is going to be changing with the internal face. It's not possible. It should be a contour. And it's going to be crashing here. Just 1 second. Maybe a little more. Now I got it. Okay. So this is how you actually check the radiation group. Just for curiosity, if you want to see inside the satellite, you just go click one of them. Okay. Go here to model browser, the tree. Let me see which node is this one. This is the tree. You go to tree and you say turn visibility off. No face. Inside it should be green, because I'm looking the inside, the internal, and you can see they are almost everyone green except the top one. So this is how I check. Reset, I'm just going to be resetting the faces. I'm going to be putting again one that I two. Let's play. My cube is there. And this face, I'm just changing. So I go to radiation, and external is actually top, and internal is actually bottom. That's it. If I do it again, model check, active display, for external, they all be green. And that's everything green. So that's how we do it. Okay. Now, for the, they are all green. Let's see. You can see it. Then I know everything's okay. Actually, you should check it for the outside and inside. So if I take it out one of the face, they should be all blue inside. But I know they are because at the time they were. If this is set right, you probably is going to be having a good result. Now the only thing missing is the orbit and actually the optical properties. When we did properties, it was conductivity properties, but I have to actually tell him the emissivity of each surface. So you go to optical properties and edit it. And here you can input any material. So it's also a little tab. It has some that I already prepared for the tutorial. And you have the solar absorptive, the infrared emissivity, and the ratio between each one of them. If you are a little familiar with radiation, radiation works in spectrum. So the radiation properties, they are not the same for the solar spectrum and for the infrared spectrum. Usually you have different configurations, okay? If you do not know which one to input, go to CubeSat or spacecraft's handbooks and then have there the radiation properties, okay? So here, if I'm going to be creating one, I'm just going to be editing one. So solar panel materials, this is properties from usually solar panel configurations. So you have here a panel for radiation properties for solar and infrared. Just to be clear, this is the ones we use for space applications, okay? If you have a spectrum of radiation, usually we use micro nanometers, okay? For the wave length. Radiation is waves, electromagnetic waves. So usually we are looking for this in this 0.4 to 0.7, if I'm not wrong. We have the light, the visible light. This is what we usually saw. So here you're going to be using the UV, and this is what we call ER, infrared, ultraviolet. This is what the sun gives us. So what we see is this little range here. What this is telling me is, what do you want as a ER, infrared? Infrared usually goes to there, here, and you have the UV and other ones to here. Solar is here, okay? So you have to set up, okay, for the solar spectrum, I have these properties. When the sun hits my solar panel, it's going to be absorbing 0.86% of the energy. So it comes 100 watts, I'm going to be absorbing 86 for the sun. But for the infrared that comes from the Earth, okay, the sun radiates in the sun spectrum, and the Earth reflects and radiates for us in the infrared spectrum. That's the difference. So you have to work with this one, with these two, the solar and the ER, because this one is going to be receiving sun, and this is the solar spectrum. But it's also, if you have the Earth, since the Earth is usually Kelvin is the basis, it's going to be emitting radiation in the ER spectrum. So you have to set both of them, okay? For the infrared, I'm using 0.82. These values you have to look in the handbook, okay, for spacecrafts. You have transmissivity, I'm not using. This is specularity. It's for, this is a diffuse configuration, okay? And this is gray. Specularity is when you have a laser, it hits like this and goes in the same angle. Usually, when you are using solar applications, they are diffuse. If you have the sun coming, usually comes like this and reflects in all directions in the same pattern. This is diffuse, okay? This software, it applies to diffuse applications and specularity applications used for mirrors or something like this. Space applications are usually diffuse, except if you are using reflective lens, okay? It's not the application here. So the default is diffusive. So this is the diffusive value. And this is a diffuse domain. In infrared, he's using the gray surface assumption. If you know radiation, you know what I'm talking about. I'm not going to be describing here, okay? But this is an important assumption for radiation applications. In this software, the default is gray assumption for gray surface for infrared, okay? Is the default. If you do not want this, you have to go there and change it. But usually for space applications, the one we use, okay? So this is the radiation properties. They are okay. Then when I double click here, just let me reset here. This solar panel material that I said for the radiation, it comes from there. The solar panel material is the one that I show you, 0.86 for solar and 0.82 to infrared. This is how I can say, no, this is white paint, this is metal, this is solar panel. You can actually choose here, okay? This is a simplification, okay? You have top solar panel. The correct one should have bottom other thing. The inside of the satellite is not solar panel. It's something else, okay? So you should have a white paint or aluminum or something else. But this is a simple example. It's not going to be having much difference. I do that to each phase. Now I have correctly told the software only thing missing is the orbit. Now we are going to put it in orbit, okay? This, until here, the software understands what it has to do for heat exchangers. This is, now we just go to orbit. You go to thermal, and you have a label here, orbit. The thermal desktop has already orbit radiation calculations for classic orbits for you, okay? So you can actually just say, I want this orbit. This is why the software is used for space applications. It's already prescribed. So you go to orbit, and you have a lot of things here. I'm going to manage orbits. Manage orbits is, I'm going to say to him, you're going to be doing an orbit. Usually, he already has a basic one. He'd say, okay, you want an orbit? I'm going to call it orbit. It's a basic one. I'm just going to be using one. So I go there, edit. Okay, I'm going to be telling, okay, it's an orbit, but you should have the configuration I want. You can see this is a default configuration for him. I don't know if you can see right, but this is 0 degrees beta angle. This is the angle of the satellite with the sun. Okay? Beta angle and altitude. This is 430. This is International Space Station, almost. Okay, this is altitude. So here you can set any orbit that you want. For this application, like I said, I'm going to be setting a simple one. It's what you call a 30 degrees. So you have the Earth, the Ecuador, and I'm going to be using something like 30 here. And here we have the sun. And this is, I'm going to be setting 500 kilometers. It's normal orbit, okay? Altitude of the space.
Esse ângulo, a senhora falou que em relação ao Sol, o ângulo que a gente utiliza para o lançamento é o ângulo...
Inclination. It's not this, it's a little tricky because we have the inclination angle, okay, for the orbit plane. I want to launch the beta angle. Sometimes it's the same value. If the Earth is like this through the year, we have the summer and winter. So the Earth actually, when it rotates, it actually inclinates a little, upside and downside, okay? When we have this, if you call it, this is the Ecuador. We are almost here. This is the Ecuador. When the Ecuador is actually aligned with the sun, in this configuration, the beta angle is actually equal to the inclination, only in this configuration. But this happens once in a year. Once in I don't know which month, but in 1 month, this happens. Usually the Earth, it goes a little up and a little down. So this, let's say you have July here. It's not July, okay? It's just an example. In July. This is the configuration of the Earth for July. Then you go to December. You probably are going to be having something like this with the equator. I don't know in English, but in Portuguese it's solstício, de inverno. We have the configuration. When you have this, your inclination is based on this angle. The beta angle is based on this reference. So you're going to be having an inclination of the satellite different of the beta angle. For this, to understand which one, you have to understand a little of orbit configurations.
So, if you specify the beta angle, it's just for a small period.
Yes, you're right. Yes, you're just you're correct. That's very good because what the software lets me prescribe beta angle. We usually use the software for the hot case and cold case. When you do a satellite analysis, usually when how is the life cycle, okay? I'm going to be launching January 2025, and it has 1 year of lifetime. So he's going to be on air, on orbit, until December. Then I have to actually analyze what's my inclination during the launch. In January, the inclination was 98. So I go to our orbit software, and I go, okay, for 98 in January, this is a beta of, usually in January, you're gonna have, if you have a 98 inclination, you're gonna have a beta of almost 70. Almost, depending on the year. Through the year, this beta is going to be changing until 0 and until minus 70. This is actually what we have usually in 1 year. Depends a little of the inclination, but this is a common inclination for satellites. To know which beta, you have to actually calculate the orbit, propagation of orbit. You have the STK, the software, STK, it does that, okay? Or you can have an open access and calculate. It's not so hard, it's not my area. It's hard for me, because it's not my area. But for the ones who study orbital mechanics, that's actually really easy to do, okay? Not my expertise, but I know that's easy to do. The software, what it has is usually when you have this range of beta angles, one of them is gonna have the hot configuration, we say, the most critical for high temperatures. And one of them is gonna be the cold configuration, where you have more colds. Usually you use the software to the hot beta and cold beta. Or you can actually run for different configurations. So you actually, if you're doing a real job, a real project, you have your first job is to find the right beta, okay? Or just try everyone, all of them, okay? You can actually try all of them in plots, and you can see, this is the hot, this is the cold. In this configuration, I'm using a basic configuration of 30, because usually it goes from 70 to -7. So 30, it's a common configuration, okay? And altitude of 500 is a common for satellites, but you could choose anyone, each one, okay? So this is the one. You can see he has here calculated the period of the time. So here he says, okay, to have 500 kilometers and 30 degrees, you have a period of 5,676 seconds. This is the time the satellite takes to round the Earth. 90 minutes usually, okay? So it calculates. This is the basic information. I want this basic orbit, okay? You go here, okay, orientation. This is another orbital orientation. For the ones who use satellites, the satellite can behave different in orbit. When you do control, for orbital control for the satellites, you can actually make it have one face always looking the Earth, or one face always looking the sun, or it can spin, or it can rotate. You actually use components to make it behave as you need it to behave. Let's say you are going to be using a CubeSat for pictures, to take pictures from the Earth. So you want this one of the faces always looking to the Earth, okay? This is a behavior. The most common behavior is the one we call nadir. So in the thermal desktop, you have to tell him, you are going to be behaving in this type of behavior. I want a nadir behavior. I want a spin. You can rotate. He does everything. You just have to tell him, okay? So I'm using here what we call a nadir comportation, or a nadir behavior. It's the most common for pictures. You use it, usually you use magnetox, I think we call it in English, magnetos, for control this. So you always have one face looking for the Earth. So this is the nadir configuration. You could use the others. So this is my satellite, this is Earth. I'm going to say, okay, this face is always looking. So when it goes like this, it goes looking. So the CubeSat rotates to make this face always look. This is a nadir component, nadir behavior. You can choose the face. So I'm telling you, the face plus Z is the nadir. This is the face is going to be looking the Earth. You can set everything you want, okay? So you have nadir, you have sun, one face always looking the sun. The star, if you have a configuration for stars, and so on. This is the most basic, the nadir, okay? I could set other configurations, the spin. I'm not going to be setting spin. Usually you have to predict if you are going to be you usually have a spin in orbit. You have to control it, or you have to predict it, okay? And here is just here showing me, okay, I'm going to be using starting 0 degrees, and then I go around 360. We don't need to exchange nothing. Here is a basic comportation, okay? If you need to input planetary data, this is for Earth, okay? So you have the radius of the Earth, the gravitational mass, and so on. This is default, all right, for Earth. The solar configuration, this 1354 watts meter square. It's the radiation flux from sun, usually the ones we use, okay? You can change it if you want, but this is the default, okay? Albedo, we call it, it's the sun. It actually, when you have the sun, the radiation hits the satellite, but the satellite is very small. So the radiation of the sun also hits the Earth, and the Earth reflects to the satellite. We call it albedo, okay? This is albedo. And this, he's asking me, okay, how is the configuration for reflection of albedo from the Earth? 0.5, it's a common configuration for this type of reflection. Usually, you do not need to have a constant value. When you have ice, you have something else, it reflects different. But this is a configuration very default. This is the infrared from the planet. The planet, since it's not 0 Kelvin, it emits infrared configuration. Usually we have the temperature of 250 as configuration for Earth. This is a very common temperature. It's not that the Earth is at 250, otherwise it would be cold. It's just for the radiation behavior for infrared. It's equivalent for a, how we call it, a black body of 250 Kelvin, okay? This is a very common default configuration for Earth as black body. The sun, if I'm not mistaken, it's considered an equivalent for a black body at 5,000 kelvins, if I'm not mistaken. Anna? No? You actually you know? No, the sun? It's 5,000, I think, Kelvin.
Yeah.
Yeah.
It's
1,080
Kelvin.
In here, you could set spin if you want. I'm not going to be setting spin, okay? And if you want to comment. So this I just input, okay, this is a basic orbit of 30 degrees. And now I can display it. And he's trying to show me, okay, this is what you have inputted, okay? So you have this, I'm going to be zooming in. You have the Earth. You have a representative of the satellite. This is actually not in real scale because the satellite is very small. But you can see he's telling me, okay, this is the satellite, this is Earth, okay? And this, it's a shade. This is the shade of the Earth. So the sun is here. And you can actually see if this is the orbit you were looking for, okay? This is the start point, but I can actually make it an animated orbit just to check if this is the one I'm trying to see. So here, I go to animate, okay. And he's, yes, you have always the same face looking to the Earth, and he's rotating in 30 degrees. If I actually try to look from the side, you can see the 30 degrees. This is at 30 degrees. This is a configuration. The sun is coming here. So this is the 30 that I've inputted. So this is what I wanted him to do. The face is always looking at the sun. That's the orbit I'm inputting. If you input something else, you can check here. This is what he's supposed to do. Now everything's right, just to go, okay? This is just a visualization. So I go, there is a little there, go reset. Just go back to my model. And now we are going to set it to go. So to set it, I have now, everything is ready. I just have to go here and say, okay, let's solve this. You can create different cases because this is a software you can create and compare different cases of orbit, okay? I'm just going to be running one case. So I just call it case orbiter. And I'm going to be editing what I wanted to calculate. So go to edit. And we have a lot of things here. Most of them are default. So you can see he's asking me, do you want to calculate radiation? Where I'm going to be writing this information and so on. This is all default, okay? Here, I'm actually telling you, this is a steady state or transient. Transients that varies with time, usually what we are looking for to see the orbit, okay? But this is double checked, so we have a steady state. Just so it starts, let's say like this, the software is just a calculation. So if I just say transient starting 0 and go to any time, he's going to be starting at a default temperature of 293 degrees Kelvin. And then he goes up, and it takes a few orbits to stabilize what would be actually the behavior in orbit. If I just preset as a steady state, it's actually going to be starting from the same temperature, but it's going to be running a few orbits, and then he's going to be actually showing me the results after the orbits have a periodic behavior. And then he goes my transit. Okay, this is what I'm setting, because you can actually see after the launch a few orbits. I'm going to be starting 0 time. The end time I've just set to, it's a little small, but here we have h period multiplied by 3. I want it to run 3 orbits for me. So the h period is the orbit period multiply by 3, okay? You can do that by inputting functions. So you have a lot of functions, and here you have an orbit. It actually, you can prescribe a lot of things if you are an advanced user. I just go here, okay, just use the HR period of the orbit, multiply by 3, show me 3 orbits, okay? And then he calls. He says, okay, 3 orbit was 5,900, I think. And here, radiation desks, okay? Here is another important thing. You have to set this tree. Usually, when you are going to be setting the case, you have nothing here. You have the analysis group that we call it internal, external. I have already told the software which ones are internal, which ones are external, which one is looking inside, which one is looking outside. But when I'm going to be running my case, I still have to say to him what this internal is going to be doing and what the external is going to be doing. So actually, in here, we create radiation configurations, okay? The first one is for my internal. So this one, I use the HADCADs. HADCADs is view factor. For those of you who understand radiation, HADCADs is the calculation of the view factors for radiation in exchange through surfaces. You can use it when you have a surface that always has the same view factor with other surfaces. The view factor is something like that. I have a surface here and a surface here. This distance, okay, if I'm not moving it, it's going to be giving me a view factor of 0.5. So 50% of the radiation energy that comes from here goes through here, if I do not move it. If I do something like this, but it's the same distance, it's the same value. If I do this, it's not 0.5 again. So when this value is constant, I can use this HADCAD configuration. This is a HADCAD configuration. View factors that are constant. I use it for internal configuration because the satellite, when it's moving, the CubeSat, the distance between the surface does not change. It's always the same cube. So in the internal configuration, the view factor does not change. So I'm telling the software, for the internal configuration, you are going to be using view factors for radiation. Okay? That's the idea. That's HADCAD. You can see there is a lot of configurations. You have to actually know which one you are using. Otherwise, it's not going to be calculating correctly. Because I told him to use, I told him who is internal, who is external. Okay, now he answers me, which model do you want? Okay, you have to actually input the model. So HADCAD is view factor. He asked, okay, who is HADCAD? Internal. Internal for me. Internal is the configuration HADCAD. Calculation method, Monte Carlo. It's the one of the most common. Okay, you do have another one, but Monte Carlo is the most common. He's going to be shooting rays, a lot of rays, and he's going to be understanding, okay, this one hits the surface, this one does not hit the surface, and then he calculates. This is the first thing. This internal is view factors that are constant. Okay, how many rays do you want? 5,000 rays. Each surface is going to be, each node, that in this example, it's one surface, is going to be shooting 500. If you use more rays, it's more precise, but also takes more. If you want to have a fast calculation, you do this simple configuration. 5,000 is a good number. Okay, I don't need more. It's going to be the same. So each node is going to be shooting 5,000. Okay, this is the error configuration if you want to speed your convergence. And this is it for the internal. There is another tabs. You do not need them because they are tabs for advanced control. If you have a convergence problem, a complex geometry, and for some reason there is a problem in the radiation calculations, okay? It's not the, you should have an expert confirmation here. So the internal, it's view factor. Okay, in the external, you have two configurations for external. The first one is the orbit, okay? I have prescribed the orbit, but I have to tell the software that the orbit is in the external part of the problem, not in the internal, because he expects me to say. So in the external, I say, okay, you're going to be using, I'm the wrong tab, sorry. ratings. So this is a prescribed heat flux. For the external, you're going to be using heating rates. This is prescribed heat flux. Is the sun and the albedo, okay? Where? External. It's the external phase, okay? Which heat flux? The orbit, because I could use any heat flux, okay? But I've prescribed the orbit because I want to use it. So use the orbit. The same thing, Monte Carlo, how many rays? The orbit is a little more complex, so I'm using 1 million rays. This is a common number for external orbits because you need more precision for external orbits, okay? So I'm using million rays. And which sources do you have? Solar, albedo, and this one I cannot read it. It's planet shine. The sun, the reflection of the sun in the earth, and the earth itself is the trick that we use for solar applications. So, okay. And we have one more. If you look here, we have two external. Just a minute. Yeah. Okay, I've said that internal, you're going to be exchanging to view factor. External, you're going to be getting heat flux from the sun. But the external also has to emit radiation. The heat balance for any surface, it's everything it absorbs and everything that emits. The sun, the orbit, it's only incoming. I have to prescribe the outcoming from the surface for the outside. So for the external, I have two radiation compartments. External, I have the heat flux incoming, but I have the emission from itself. And this is view factor also, because it's a cube that emits to the space. The space, even if the cube is rotating, the space is everything that's outside. So the view factor for the cube to the outside, it's constant. So we do have a HAD-CAD model, a view factor model for the emission only. If you do not put it, it's going to be running with no emission. I'm going to be showing you later what happens, okay? So this is the external. And now it's the same thing. It's HAD-CAD, view factor constant for the emission of the satellite. Monte Carlo in 5,000 rays. That's it, okay. Now I have my configuration, everything's okay. You can have other things for inputs and so on, but we do not need it. We just have to set the transient and radiation. And this is okay, and now I'm going to run the case. This is the configuration running. You can see it's very fast. If you have already done orbit calculations, it usually takes a little time. So the software is very fast because he's actually made for this. He goes to the post-processor. Okay, he's telling me, okay, you have successful. If I actually had something wrong, or if I missed something, it would be not successful, and it just crash. Okay. So okay, he's telling me, okay, everything is okay. Here's the color code for this configuration. We have the configuration here for the temperature at time 7,000. It's a transient, so I'm looking for a picture. This time is a picture. Usually we are interested in the orbit configuration. So I actually go and just mark everyone, all 6 faces. And this is my maximum and minimum temperature for 3 orbits for this case. So you can see here, he's indicating each one. Remember, I called the nodes 1, 2, 3, 4, 5, 6. It's each one of them. Yeah? This is the time. So you have the 17,000, 3 orbits. Okay. You can see the 3 orbits here. Here it starts in the middle orbit. Here's actually the same. Huh? You finish here inside. So you 1, 2, 3 orbits. And you can see each panel for temperature. And you can see here there is one of the panels it's lower. This is the nadir, the one that I've said always look for the Earth. When you look for the Earth, you usually don't get much sun, so you don't get so hot. Okay, and these other ones is the ones that actually see a lot more sun. and usually this is what you're looking. And from here, you actually analyze the behavior. This is a simple case for one node. I'm going to be showing you now if I input a battery and more nodes. We are not going to be doing step by step because we do not have time. Okay, the step by step is until here. If you do all the steps, you understand this configuration, you can actually do any models. This is a very basic one, but just to show what the software can do, a more complex configuration is the one that I've opened first.
No gráfico, as faces mantiveram no Z mais uniforme, porque a gente não configurou anteriormente a questão da rotação do...
Aqui, this satellite is not spinning. If you input spinning, usually you will have a more uniform temperature. When you do not have spinning, usually you have a higher temperature and lower temperature.
Ok, aí no caso, só em caso de estudo específico. Na realidade, não.
Yes, this case is valid for this configuration. If you actually want to do a real case, you should actually first look for the betas, which are the cold beta and hot and cold beta for you. What is your orbit configuration? It does have spin, does not have spin. Which face is looking the sun? When you prescribe everything there, it's going to be really realistic. This is a realistic, it's a true solution, a very precise solution, but for this simple application, okay? But actually, we do, this software is used for complex applications. So you can go crazy. You just have to know what you have to prescribe. You have to have this information before, okay? This is a configuration with more nodes, so it's still one U, but you have 9 nodes in each phase, just to show you that battery has a constant heat flux. I'm considering the battery is always on, okay? So actually you have an input from the battery, and when I actually run this configuration, it goes like this. You can see that even with more nodes, the picture is not uniform, but in each phase is almost the same because the satellite, it goes slowly. So it actually, it's not so transient. And now if I go and plot the temperatures, you can do a lot more plots, okay? This is the very first plot. You can see everyone. So you have the maximum for each one of them. So here you have the solar panels and you have the battery radiator, okay? So also 3 orbits, so you have 1, 2, 3, and that's the beginning of the other orbit, but you have different configurations of temperature. I'm just going to be showing you, not when we don't see all panels, I could actually choose just a few panels. I'm just going to be showing the battery. You can see this is the battery. It's a simple battery with 1 node, and it's in the lower part of the satellite. And this is the temperature of the battery. Okay, so this is a battery with always on. You can actually prescribe an on-off behavior, and you can actually analyze. And you see if this is too low or too high temperature, and to analyze if the components it's within the temperature limits. So you can do a lot of configurations. Okay, the important step, just to finish, is the radiation calculation. You have to actually understand the little radiation to input the configuration of the radiation analysis correctly. Otherwise, it's not going to be working. And just to finish, what I said about the radiation, if you forget to set one of the radiations, here are the radiation tasks. I'm just going to take it off the emission. This is actually usually one of the common mistakes. or processor failed. If you get something wrong, anything that you just put it on, it fails. And this is actually the crash. It's very hard to understand what did you do wrong. Okay, so each steps in the same order to. So this doesn't happen because we do have very few material about this software online. It's very closed. It's very hard to find material. Not like other softwares. If you look for YouTube or something like that, you do not have tutorials. You do not have very things available. So it's very hard to understand where did you miss it. Okay, if you follow this tutorial step by step, it's going to work. If it's the result that you want, I don't know, but it is the step that you should do. Okay, that's the idea. Well, guys, this is what I've prepared to show you a little, okay? The software is very good for space applications, but it does have a big learning curve, so you can actually use it correctly. I hope the tutorial helps a little in that, so you can actually remember I have to do all these steps, understand them, so it goes right. So you can actually start working with them if you have the interest. And that's it. I thank you very much. I don't know if anyone has any question. I'm a little late, as always. But if anyone has any questions, you can answer now or later if you need. Okay? Thank you. Thank you. Obrigada, pessoal. Da minha parte, fechou, pessoal.